We have learned that a stress state can be comprehensively described by a 3x3 tensor. This means if we want to draw contour plots for a stress state, we need to draw 9 of them. You might come up a question that, this seems to be a lot of information for one point of a domain. Is it possible to use one value to represent the stress state of a material? That way we only need to draw one contour plot to view the stress. The answer to this is yes. We can convert the 9 components of a stress to one scalar and use it as an equivalent stress. There are many different ways to do this. Here we're introducing one widely used equivalent stress, the von Mises stress. Another very important usage of the equivalent stress is engineers use it to determine if the materials reach a certain state, such as yield point or failure point. Let's have a glance of how to find the von Mises stress from a given stress state. You can calculate the von Mises stress directly from the 9 components of a stress tensor, or you can calculate it from the 3 principal stresses. These 2 expressions yield the same equivalent stress value for one stress state. Here, let's expand the von Mises stress in the principal coordinate system, because you will see it's a good way to expand the feature of such equivalent stress. A quick observation of the von Mises stress in principal coordinate system. We can see that in the 3 brackets of the expression, the terms are basically the differences between the 3 principal stresses. In fact, this expression can be plotted as a geometric surface in the principal coordinate system. The principal coordinate system uses the 3 principal stresses as axes, and the von Mises stress can be visualized as a cylindrical surface here. The axis of the cylindrical surface is the triaxial line, where the 3 principal stresses share the same value. This axis is also called the hydrostatic axis. A very important feature to point out here is on one cylindrical surface, all the locations have the same von Mises stress value. So we have a location A on the surface, which is a stress state with principal stress value 100, 98, and 96 ksi, and another location B on the surface at the stress state with 4, 2, and 0 ksi. Although the principal stress values are in different scales, the von Mises stresses from the 2 states are calculated to be the same. The main reason for this is for the 2 locations, the differences between the 3 principal stresses are the same. You will also find that the height of the cylindrical surface is not bounded, meaning the 2 ends of it extend infinitely. This means no matter how large the value of the 3 principal stresses are, the von Mises stress remains to be the same. Then, how does the cylindrical surface reflect different values of von Mises stress? Actually, it's captured by the radius. For larger von Mises stress value, the radius of the cylindrical surface will expand, and for a smaller von Mises stress value, the radius will shrink. A very simple example to display the features of von Mises stress. Say we have a small metal cubic and we throw it into deep sea. With increased depth in water, we know that the pressure on each surface of the metal cubic will grow. But do you think the metal cubic will distort a lot or even break in water? Intuition tells us that it won't easily happen. Why? The reason is the differences between the 3 principal stresses remain to be the same while sinking in the water. The principal stresses over the face of the cube are basically pressure from buoyancy force. Let's ignore the chance of buoyancy force caused by the dimension of the cube, since compared to the water depth, it's quite small. Although the value of the stresses grows while sinking in the water, the 3 principal stresses remains almost equal to each other. Hence, in the formulation for calculating von Mises stress, the 3 differences terms are 0. If we plot the stress state on the principal coordinate system, we will see that the cylindrical surface for 0 von Mises stress is minimized to be just the hydrostatic axis. And the point of the stress state slides from origin with principal stress are all 0 to a location far from the origin with large stress values. This corresponds to the process that the cubic sink in the water with growing depth. In summary, we can see that Only when the differences between the three principal stresses change, the von Mises stress will be affected. And that's why von Mises is a good equivalent stress to represent the distortion of a material instead of the absolute value of each stress component. Engineers use this simple scalar value to compare with material stress and determine if the material has yielded or failed.